Hi guys, this is 5.1 polynomial functions. So we have added, subtracted, multiplied, and divided, factored, and solved polynomials. In this unit, we're going to look at them as functions and analyze their graphs. Okay, so 5.1, we're going to go over the characteristics of polynomial functions as graphs, and then 5.2 is just graphing them. If you're comfortable with Desmos, you might not even need to, you might be able to work through 5.2 without even watching the lecture video. Okay, so here we have f of x equals 5x to the fourth minus 3x cubed minus 7x squared plus 2x minus 8. This is an example of a polynomial because poly means many, and we have many terms here. Good. 1, 2, 3, 4, 5 terms. We have separated the terms by with operations minus or plus. Good. Okay. So a polynomial function is the combination of monomials. Monomial means one, where poly means many, more than one. One number with a positive integer exponent that is greater than or equal to 0, positive integer exponent, and having no variable in the denominator of a fraction. Okay, so we can have positive integer exponents greater than or equal to 0 and no variable in the denominator of a fraction. So it's a polynomial if it excludes anything that would have a variable in the bottom of a ratio or in the denominator of a fraction, and anything that would make the exponent of that variable a fraction. Remember that an exponent that's a fraction is the same as putting that exponent under a radical. Okay, so we're going to exclude anything that has a ratio with the variable in the bottom and exclude anything that has an exponent that's a fraction or that has a radical, an exponent under the radical, or sorry, a variable under the radical. Good. So integer exponents means we have to exclude a fraction exponent. Good. All right, so standard form. Standard form is the way you want to leave your polynomial function. It's arranged with your exponents in descending order. Remember, the exponent is just a little number up here. So descending means we go from 4 to 3 to 2 to 1. And then your constant is actually, you could consider it as being multiplied by x raised to the 0 power because x raised to the 0 power is 1. Good. So descending order just means 4, 3, 2, 1, 0. And it's okay, I'll skip 1 here. It's okay if you're missing 1, but the ones that you have should be in descending order. Good. All right, the term is the number of monomials separated by your operation symbols, the operation symbols being plus or minus. Okay, so after you have put your polynomial function in standard form, the first term will be your leading term. Your leading term should be connected to the variable with the highest exponent, okay? So for example, here we have 5 terms, not because of that number 5, but just because if we count them, 1, 2, 3, 4, 5 terms. And our leading term would be 5x to the fourth. Good? For a coefficient means that we're just talking about the number. So 5 is the coefficient to 5x to the fourth. What is your variable being multiplied by? Or 7 is the exponent to negative 7 would be the coefficient of negative 7x squared. Good? Your constant, just like in all of the other examples in this course, your constant is your number without a variable. Your constant is always your y-intercept. Good. Your degree is the largest exponent, so your leading term is going to have the largest exponent, and that's going to be the degree of the entire polynomial, okay? For a graph to be a graph of a polynomial function, the graph needs to be both smooth and continuous. This graph is smooth and continuous. This graph is neither smooth nor continuous. It breaks here, so that would be an example of breaking or a gap, and it has corners or cusps in it. Holes, corners, cusps, and gaps are examples that make it not a polynomial, okay? We're going to use this information to analyze the graphs of polynomial functions. So for example 1, they're just asking us, which of the following are polynomial functions? And if they are, write them in standard form and tell us the degree. If they are not, say why they are not polynomial functions. Sound good? Okay, so let me number them. I'll call this one 1, 2, 3, 4, 5. I guess I could just name them, right? P of x. Anyway, so for number 1, we have 4x cubed minus 1/2 x squared minus 7. Notice that even though we have a fraction, the x is not 1 over 2x squared, or negative 1 over 2x squared, is not the same as 1/2 x squared. It is the same as 1/2 x squared, or sorry, negative 1/2 x squared. Negative 1/2 x squared is actually the same as that x being in the top of the fraction, or the top of the ratio, okay? So when you see the x on this side, it always goes with the numerator, so that is okay. Even though there's a fraction, the x is in the numerator, so that is still a polynomial function. So it is a polynomial function for those that are right in standard form. So the standard form of this just means that we want to put the exponents in descending order, x to the third, x squared, and then our constant, so it's already in descending order or standard form. And then the degree, if we look back on what it means, the degree is the largest exponent. So here we have degree for 5x to the fourth minus 3x cubed minus 7x squared plus 2x minus 8. It is a degree 4 polynomial. Or you could say a polynomial of degree 4. Oh, I'm sorry, you couldn't even see that. Your degree is your largest exponent, so this largest exponent is a 4. So this would be a degree 3 polynomial. Good. Number 2, x plus 3 minus 5x to the fourth. The two rules are we cannot have our variable in the denominator, and we cannot have a variable raised to a non-integer, so to a fraction. I'll just say 1 over b. Good? Neither of those are occurring here. There is no fraction, and there is no radical, okay? So it is a function. They want us to write it in standard form, so that just means make those exponents descend. So it's going to be f of x is negative 5x to the fourth plus x plus 3. So just note that I kept the negative sign with the 5x to the fourth. I kept the x positive with the plus sign, and then I put the constant at the end, and it's of degree 4, just because 4 is the biggest exponent. Number 3, as we discussed, we can't have a variable raised to a fraction. Remember that a variable under a radical, or any number under a radical, is the same as raising that to a fraction. If you were to turn it, you can turn radicals into exponents. So x to the third is actually, or sorry, the cubed root of x is actually x to the power of 1/3. So this is not a polynomial function. Number 4, h of x equals x to the third minus 2 divided by x to the fourth plus 1. Again, this is a ratio. A ratio of polynomials is not a polynomial function. Good. Our last one, we have h of x is equal to negative x to the third multiplied by the quantity x minus 3 squared. Okay? There are no radicals. There are no exponents that are not whole numbers. There are no exponents that are negative numbers, and there are no variables in any denominators. So this is still a function. It's not in standard form yet. If it's in this form, we need to use our algebra skills to multiply it out and then put it in order, okay? So negative x to the third times x minus 3 quantity squared becomes, I'm just going to expand it out, okay? Negative x to the third times x minus 3 squared means x minus 3 times x minus 3. I'll do these first. X times x is x squared. X times negative 3 is negative 3x. Negative 3 times x is negative 3x. And then negative 3 times negative 3 is positive 9. And then I'm going to distribute that negative x cubed. Negative x cubed times x squared. And negative times a positive is a negative base. And then if the base is the same, we just add the exponents. So negative x to the fifth. Negative x times negative 3x is a positive 3x. That was to the third, and that's raised to the first power, so 3 plus 1 is 4. Negative x cubed times negative 3x, I guess I could combine those first. Be the same thing, positive 3x to the fourth. And then here we have negative x to the third times a positive 9, so that'll just be negative 9x to the third. Good? Okay, let's add these, and what we will end up with is negative x to the fifth plus 6x to the fourth minus 9x cubed. Okay, an important note is right now you have no constant, or your constant is 0. And remember, your constant is always your y-intercept, so this would have a y-intercept at the origin. And you are also welcome to graph any of these in Desmos to see their characteristics better and see if they are smooth and continuous. Okay, so example 2 asks us what graphs in the figures below could be the graph of a polynomial function. Again, if it is a polynomial function, you want it to be smooth and continuous. Here, we would have not continuous. At this point. And here you would have not smooth. Right here at this point. But over here, if I just try to draw it, right, it's a pretty smooth arc. So I would call this smooth and continuous. Again here, smooth and continuous. All right. The power function of your polynomial is the leading term, okay? So the power function is the leading term of the polynomial function. A power function of the degree n is the leading term of the function when written in the standard form f of x equals ax to the power of n. Good? So the graph of a polynomial function will always resemble the graph of the power function or the parent function. So we're just creating we're experiencing a parent function with some changes, right? Here would be x cubed, but then we have a -2 shift, for example, right? If this n is even, then it's going to look like when n is even, so n to the 2, n to the 4, n to the 6, n to the 8, it is going to resemble somewhat the graph of f of x equals x squared, right? If it is odd, n to the 3rd, 5th, 7th, 9th, then it's going to resemble f of x is x to the 3rd. So if it's even, your direction, or sorry, to the left and to the right, the left and right side of your graph are going to go in the same direction. If your exponent is odd, those are going to go in different directions. One's going to go up, the other one's going to go down. Good? So if the leading term is even 2, 4, 6, 8, it will take on the shape of a parabola. Same direction. On the left side and the right side. So it might be going up like this one, or it might be going down like this one. And if your leading term is odd, it will take on the shape of x cubed, which is different directions, or opposite directions maybe. To the left and right. In this case, we're going down to the left, up to the right, or it might be up to the right, down to the left. Determine the power function of f of x equals 3x to the 5th minus x squared plus 2, and then verify by graphing it. All right, so what you want to do here is determine what your leading term is so that you can find the power function of the polynomial. Good. When you see it in my math lab, the way they write it is the graph of f, the graph of f behaves like, and then they're going to give you a blank for large values of x, but we're going to call it the absolute value of x. So that's how it's going to show up, and they're going to want you to put in your leading term. Okay? Determine the power function or determine the leading term. My power function is right here. So the graph of f behaves like, or resembles 3x to the 5th for large values of the absolute value of x. Okay? And it's of degree 5 because we have the degree of the leading term. That's already in standard form. It's easy to identify the leading term in standard form, right? We can see that it's 3x to the fifth, that the 5 is odd. However, these two are not quite in standard form. You are welcome to multiply them all out completely, or there's a faster way. So if I were to multiply out x minus 2 quantity cubed times x plus 7 times 2, to get my leading term, the only elements that will actually go into the first term or the leading term are going to be this x and this x, right? Everything else will fall behind those two x's. So this x is being raised to the third power, and it's going to be multiplied by x. This x is not raised to any power, okay? So 2 is not an x, so it's not, yeah, sorry. We'll include the 2. So the 2, the x cubed, and the x. So the 2, the x, and the x, but this x is cubed. The 2, the x, and the x are your leading terms. You're going to multiply them together to find your actual leading term of your entire polynomial. So x cubed times x is x to the fourth with a 2 in front of it. So the graph of f behaves like 2x to the fourth for large values of the absolute value of x. If you were to use FOIL here, or sorry, if you were to multiply this all out, yeah, first outside, inside, last, stretch this out, multiply it by this one, and then distribute the 2, the leading, and then putting it in, ensuring that it's still in standard form or in descending order. Your leading term, or the first term, will be 2x to the fourth, but it's easier to only look at your leading terms and just multiply them quickly, because it doesn't, that's all they're asking for is the first term. C is f of x equals x times the quantity x squared plus 3 squared times the quantity x minus 5. All right, again, we're looking at just the leading terms. We have an x, we have an x, and we have an x. This x is not raised to any power. This x is squared and raised to the second power. And then this x is not raised to any power. So we're just going to multiply those leading terms. Leading term, leading term, and leading term. X times x squared squared times x. So let's say that's x times x squared squared. When you take an exponent and raise it to another exponent, you multiply. So 2 times 2 is 4. So that's going to be x to the fourth times x becomes x to the fifth times x becomes x to the sixth. So for graphs, the graph of f behaves like x to the sixth for large values of the absolute value of x. X to the sixth. Good? So this one behaves like 3x to the fifth, or resembles 3x to the fifth. This one behaves like or resembles 2x to the fourth. This one behaves like or resembles x to the sixth. Let's also talk about what degree they are. This is of degree 5. This one's of degree 4. And this one's of degree 6. We agree? I just want to go back and touch on other things we've discussed in previous pages. Okay? Now we are going to talk about something that is quite challenging compared with other parts of today's lesson. Okay? So we have our only example problem here is f of x equals x plus 5 times x minus 2 squared times x minus 4 times x plus 1. Okay? It's not in standard form because in this example we're talking about real zeros. All right? What is a real zero? A real zero is any value that you can substitute into a function and cause the entire function to equal 0. Okay? Any value r for which f of r is equal to 0. If that is true, then r is called a real zero of the function r, or of the function f. R is an x-intercept of the function f, which is true, right? An x-intercept is also a 0. And when you take that number, but you take the opposite of it and group it with x, or you subtract that number from x, you get a factor of the function. That's what that one means, okay? And, of course, f of r equals 0, so r is a solution to the equation f of x equals 0. Good? All right, so down here, if we're talking about real zeros, x minus your real 0 is a factor of f. Do we see that? So this would have an r is -5, right? Because x minus r is a factor. This is one of the factors of f of x. So my real 0 is -5. Here I have x minus 2, so that real 0 is a positive 2, because when I take the opposite of that number and combine it with x, you get a factor of the function. We also have x minus 4, that means that real 0 is a positive 4. And finally, we have -1. X minus that real 0 will be a factor. Factor. So 0, 0, 0, 0. Those are real zeros of this polynomial function. Sound good? Okay. Let's review what we have already learned about polynomials. Okay? Where's my first page? So the exponents are going to be in descending order if it's standard form. Each item separated by a plus or a minus is a term. The leading term in standard form will have the greatest exponent of the variable. Your coefficients are the numbers in front of the variable, the 5, the -3, the -7, the 2, and our coefficients. The constant is the number without any variables. It's also the y-intercept. And then degree is the largest exponent of that polynomial. So if you've put them in order, your leading term is going to have your degree. So this is a degree 4 polynomial. Good? The graph should be smooth and continuous. Sorry, you couldn't see that part. We decided this is a polynomial function. This is a polynomial function. This is not a polynomial function. This is not a polynomial function. This is a polynomial function, but it's not in standard form. We then used algebra skills to get it into standard form. Good. So down here, we're looking at not standard form, but it's still a polynomial, right? It hasn't broken any of the rules. We looked at the graphs, and then we decided, we learned about the power function, right? We will talk about what these, we'll review this later, but the power function is the leading term. So f of x equals 3x to the 5th minus x squared plus 2 is going to resemble 3x to the 5th, or behaves like 3x to the 5th. This, when we multiplied the 2 times the x to the 3rd times the x, we got 2x to the 4th. So this graph behaves like 2x to the 4th. We multiplied x times x raised to the 2nd power raised to the 2nd power times x, and we got x to the 6th. So this graph behaves like x to the 6th. Good? All right, now we're moving on to real zeros. I just don't want to overwhelm you. So let's practice finding the power function of this before we talk about multiplicity, okay? It's something we just learned. Here we have our leading terms. So if I'm trying to find the power function, I put my camera too high today. I'm not staying in the frame at all. Our power function, what we do is we take the leading terms. Here, the leading term is x. Here we have x, but it's raised to the 2nd power. And then here we have another x. And then here we have another x. So our power function here, there were no numbers. There were no coefficients with our x's. So it's just going to be x squared times x makes it x to the third, times another x makes it x to the fourth, times another x makes it x to the fifth. So our power function here is x to the fifth, or this graph resembles x to the fifth. Good. X to the understood first power, x squared, another x to the first power, another x to the first power. I multiplied them all together. I got x to the fifth. I'm changing from factored form to standard form, but only the leading term. So my leading term is going to be x to the fifth. Okay. Then they asked us to identify the real zeros. We identified that our real zeros are -5, 2, 4, and -1. Why? Because the definition says that R, if R is a real zero, then x minus R is a factor of f of x. Okay? So our factors of f of x, let's list them all, is x plus 5, x minus 2 squared, x minus 4, and x plus 1. This is raised to the understood first power, raised to the understood first power, raised to the understood first power, raised to the second power. Okay? So here, my real zero is x minus -5. My real zero is x minus +2. My real zero is x minus +4, and my real zero is x minus -1. Okay? Okay, now let's talk about, so we understand power function. The power function of this polynomial is x to the fifth. The real zeros are -5, +2, +4, and -1. Okay, let's move on to multiplicity. If x minus 4 raised to the m is a factor of a polynomial, then when m is odd, then the graph will pass through the x-axis or cross the x-axis. If m is even, then it will touch the x-axis and turn back. Okay, so identify the real zeros. We've got our real zeros. State their multiplicity. The multiplicity is this number up here. Okay, so that -5 has that -5 has a multiplicity of 1. What is it being raised to? It's being raised to the first power. This x minus 2 has a multiplicity of 2, or it's being, the entire factor is being raised to the second power. For this third one, x minus 4, it's a multiplicity of 1. And for x plus 1, that makes a real zero of -1 and a multiplicity of 1. Okay? So, identify the real zeros, state their multiplicity. Got it. Describe the interaction with the x-axis. It sounds confusing, but we can do this, okay? Describe the interaction with the x-axis. That means, does it pass through the x-axis or does it touch the x-axis? Okay? It says, if m is odd, so we know 1 is odd. We know 2 is an even number. We know 1 is an odd number. So we know that this one's odd, this one's even, this one's odd, and this one's odd. If it is odd, it passes through the x-axis at r. I'm going to call it crosses because I'm going to forget. So it crosses the x-axis at x equals -5. Okay? Even means it touches the x-axis at x equals 2. It's a real zero of 4, but it's odd. Odd means it crosses or passes through. So it crosses the x-axis at x equals 4. Here it's odd, so odd means it crosses. It crosses the x-axis at x equals -1. Okay? So x plus 5 as a factor of our function means that this function is going to cross the x-axis at x equals -5. X plus 2 squared, the squared means it's only going to touch the x-axis and then come back up or go back down. Okay? At x equals +2, it's going to cross again at x equals 4 because of this one raised to the first power. And at x plus 1, that means it's going to cross at x equals -1 rather than touch. All right, let's imagine what this means. No idea where my ruler is. I'll just say that this is x equals 0, x equals 1, x equals 2, x equals 3, x equals 4, x equals 5. Good? All right, let's imagine this graph now. What we have is a graph that crosses x at x equals -5. Ooh, let's look at what the y-intercept is. All right, it looks like if we were to multiply 5 times -2 squared times -4 times 1, we would get a negative number, right? So my constant or my y-intercept is going to be a negative number. So if I were to graph this, that means between -1 and 2, it's going to go down. All right, so we have -5, -1, 2, and 4, right? It's going to cross the y-axis at a negative number, so that means between -1 and 2, -1 it crosses and +2 it touches. So that means I'm going to go like this. At +2, it just touches and then goes back down because it comes up to touch and then goes back down, and then crosses at 4. It crossed here at -1, and it crossed here at -5. So my graph is going to look something like this. From the negative infinity up, crossing at -5, crossing again at -1, touching at 2 and coming back down, crossing at +4. So that's the point -5, 0, that's the point -1, 0, that's the point 2, 0, and that's the point 4, 0. We identified the real zeros, we stated their multiplicity, we described the interaction with the x-axis. Describe the interaction with their x-axis is these guys. Okay, let's see if this is accurate according to Desmos. We are talking about this guy. All right, so it looks like we are crossing at -5, crossing at -1, touching at 2, crossing at 4. So we can verify that that is true. That is what we mean by real zeros. Good? The multiplicity is just the number of times the factor occurs. Right? So this factor occurs one time, this factor occurs two times, this factor occurs one time, and this factor occurs one time. If it occurs an odd number of times, it passes through the x-axis. If it occurs an even number of times, then it touches and then goes back. Touches and turns at the x-axis. Touches the x-axis and then turns. Good? All right, so let's consider, hold on. Got my pages out of order, just ignore me. Example 5 asks us to find a polynomial function of degree 3 with the zeros -1, 2, and 3, and then verify using a graphing utility. Does that make sense? So if it's of degree 3, with real zeros -1, 2, and 3. So let's look at our real zeros again. A real zero is a value of r. It's also an x-intercept. And then if you combine it, take the negative of it and combine it with x, you get a factor. All right? The real zeros are -1, 2, and 3. Okay? So if my real zero is -5, that's going to turn my factor into x plus 5. If my real zero is 2, it's going to turn my factor into x minus 2. If my real zero is 4, it's going to turn my factor into x minus 4. If my real zero is -1, it's going to turn my factor into x plus 1. So let's convert our r's into factors, right? Because the rule is, once we have found r, we can say that the factor is x minus r. R is -1, so my factor is going to be x minus -1 or x plus 1. R of 2 means my factor is going to be x minus 2. R of 3 means my factor is going to be x minus 3. All right, so we have made our... All right, so we have determined our 3 factors, and we know it is a polynomial of degree 3. So that means that the highest power our leading term could have is the 3rd degree. X plus 1 times the factor x minus 2 times the factor x minus 3 would give us a factor or an entire function and a leading term of a degree 3 polynomial. The leading term would be x to the 3rd. So we're just going to say that the answer is f of x equals the quantity x plus 1 times the quantity x minus 2 times the quantity x minus 3. Okay? So if they ask you to find a polynomial of a degree and give you a number, and then they give you the real zeros, translate the real zeros into factors, and then ensure that when you multiply those factors, you get the correct number of degrees. If not, make one of them into a raise the power of one of the factors. When they ask you to verify using a graphing utility, that just means take the polynomial function that you found. So in this case, it would be x plus 1 times quantity x minus 2 times quantity x minus 3. Make sure that it's a degree 3. Make sure that it has the real zeros of -1, 2, and 3. We know it's a degree 3 because x cubed has the same pattern. There are 2 terms in x cubed, and x cubed goes from left to right in opposite directions. So it starts at the negative y on the left, and then it ends with positive y on the right. So that's what it means by verify using a graphing utility. And we proved that the real zeros were -1, 2, and 3. Okay. For example 6, it asks us to find the real zeros and state the multiplicity, decide if the graph will touch or cross the x-axis, and then also verify. So we have 3 terms here. We have the term 6x cubed. We have the term, the factor x minus 5. So we have the factor 6x cubed, we have the factor x minus 5, and then we have the factor x plus 1/4, right? This one's to the 4th power, and this one's to the 3rd power. What are our real zeros here? So our real zeros, it says you take the opposite of it and combine it with x, but really we're solving it for x. Okay, so another way to look at the real zero is set it equal to 0 and solve for x. So here we would take 0, we would divide it by 6, and then we would take the cubed root of it, and we would get that r equals 0, right? X minus 5, we would say that our r is 5, right? 5 minus 5 would give us 0. 0 cubed times 6 would give us 0. X plus 1/4 equals 0. So my r is going to be negative 1/4. So my real zeros are 0, 5, and negative 1/4. What are my multiplicities? The multiplicity of this one is 3. The multiplicity of this one is 1. And the multiplicity of this one is 4. 3 is an odd number. 1 is an odd number. 4 is an even number. Good. So if your multiplicities are odd, then they will cross the x-axis at, and don't use your multiplicity, it will cross the x-axis at your real zero, cross the x-axis at x equals 0. Sometimes I get them confused and say x equals 3. Odd means it will also cross the x-axis at x equals positive 5. Even means it will touch the x-axis at x equals negative 1/4. Let's verify this using a graphing utility by going to Desmos, putting into Desmos 6x to the 3rd times x minus 5 times x plus 4 plus 1/4 to the 4th. It will give us a 0. Sorry about that. All right, so we see that it will either cross or touch at negative 0.25, negative 0.1076, at 0, and again at 5. So we found the real zeros. They were at 0, 5, and negative 1/4. We stated their multiplicity, and we decided if the graph would touch or cross the x-axis. I think they were supposed to be. All right. Example 7. Consider the polynomial function f of x equals x minus 3 squared times x plus 4. Good. Find the real zeros and state their multiplicity. Good. So we have r of 3, and we have an r of negative 4. The multiplicity when r equals 3 is 2. The multiplicity when r equals negative 4 is 1. Find the y-intercept. Okay, so just like we can find the leading term by only multiplying the leading term of each factor, so the leading term would be x squared times x is x to the third. The y-intercept is the same as your constant, and you can find that by multiplying each of your constants. Okay, so my constants are -3 cubed, or sorry, -3 squared and +4. Good? All right, -3 squared is 9, and 9 times 4 is 36. So my y-intercept is x equals 0, y equals +36. Good? We can check this on Desmos. -4, 3, and 36. Turning points. All right. Turning points are points where the graph changes between concave up and concave down. The max number of turning points a graph can have is one less than the degree of the polynomial. So your max number of turning points is just your degree minus 1, okay? So to determine the number of turning points a graph can have, we just find the degree by taking the leading term, x to the first, x squared, x, and x. So my leading term is x times x squared times x times x, x squared times x, third, fourth, fifth, x to the fifth. So my degree is 5, and the max number of turning points is 5 minus 1, so number of turning points is going to be less than or equal to 4. Oh, sorry, you couldn't see that. If it's a degree 5, it has 4 turning points or fewer. Now let's talk about the end behavior of graphs. The end behavior of a graph of a polynomial function is the same as the graph of the power function. F of x equals ax to the n. If a is positive, or your leading coefficient is positive, the graph opens up to the left and right, or up to the right. If your leading coefficient is negative, the graph opens down to the left and the right, or down on the right. If your exponent is even, the ends of the graph go in the same direction, and if your exponent is odd, the ends of the graph go in opposite directions, okay? So this would be the graph of a positive, even, a positive leading coefficient, and an even exponent. So positive x squared, positive x to the fourth, positive x to the sixth, positive x to the eighth. Positive to the left, positive to the right. Good. This one shows the exponent is still even, so the ends of the graph still go in the same direction, but these are negative directions, so negative x squared, negative x to the fourth, negative x to the sixth, and negative x to the eighth. Good. Now they are going in opposite directions, so those are not even exponents anymore. If your leading coefficient is positive, the graph opens up to the right. This one opens up to the right, so that is going to be positive, but my exponent is now going to be odd. So x to the third, x to the fifth, x to the 7th, x to the 9th. And then obviously our only final option is if a is negative, the graph opens down to the right, so that's a negative odd. Okay, there's also kind of like a table you can make. So here is my degree of my polynomial, and here is the positive or negative value of my leading coefficient. So if my leading coefficient is a positive number or a negative number, and then if my degree is even or odd numbered. Good? All right, so if I have a positive leading coefficient and an even degree, then to the left and to the right, it will be moving in a positive direction. If I have a positive coefficient, but it's an odd degree, then it will be going up to the right, but down to the left. If my leading coefficient is negative and it's even, they will both be going down to the left and to the right. And if my leading coefficient is negative and it's odd, it's going to be going down to the right, but it's going to start up to the left. Okay? If that helps. Maybe that helps, maybe that helps. But that's called end behavior. So we're talking about what the exponent of the variable is doing and what the leading coefficient sign is, positive or negative. Okay? Page 10 asks us, what graph of the figures could be the graph of f of x equals x to the 5th plus ax cubed plus bx squared minus 2x plus 3, right? So you can't really put this into Desmos because Desmos isn't going to graph something with an a and a b in it as well as an x, right? There's a little bit of mystery, so we have to use the skills we've learned today to figure out what, as much as possible, what this looks like. Good? So we know that if our constant is a 3, that means that our y-intercept is 3, so it's going to cross at 0, 3. Okay? And then what did we just learn about end behavior? It is so we're just looking at our first term. For end behavior, you're looking at you're making sure it's in standard form, which it is, and then you're looking at your positive x to the 5th. So x to the 5th would fall into the category of positive leading coefficient, odd exponent. So we're going to be going down to the left, up to the right. Down to the left, up to the right, because it's positive x to the 5th. Down to the left and up to the right because of x to the 5th. Also, for turning points, it's a degree 5. So it has 4 or fewer turning points. So we are looking for a graph that turns 4 or fewer times, that crosses the y-intercept at 3, and that starts to the left negative and ends positively to the right. Okay, so let's count the number of turning points. 4. 1, 2, 3, 4. 1, 2, 3, 4. Way too many, so we're going to eliminate that one because of the turning points. 1, 2, 3, 4. The rest are okay. All right, let's look at crossing at positive 3. This one does not cross at positive 3. That one might be crossing at positive 3. That one might be crossing at positive 3. Okay, and finally, we're going to look at, does it begin negative to the left and end positive to the right? This one does not. Okay, so I'm going to choose this as a potential graph of x to the fifth plus ax to the third plus bx squared minus 2x plus 3. Good. All right, I think that's the end. Thank you guys. Sorry about all those interruptions. There were a lot of children in the room.